Hello everybody, this is Dr. Christopher White, and in this lecture we will be looking at deformation. Alright, let's get going. So what are we going to be trying to achieve? Well, over the next few lectures we are going to be investigating the processes of deformation and metamorphism, and we're going to be thinking about the rocks and structures that they produce. We're going to try and understand the plate tectonic setting of deformation and metamorphism, and we're going to observe how structures and metamorphic rocks are expressed in the landscape. Alright, so this of course is our rock cycle diagram. You are all very familiar with this by now, so let's just skip through the basics. Of course we have exposed rock. The exposed rock gets weathered. The resulting sediment gets transported, during which of course there's erosion. The sediment eventually gets deposited. Eventually the layers of sediment are produced by deposition, get buried. They get lithified of course to produce sedimentary rocks. If you keep burying them deeper and deeper, eventually of course they will get exposed to increased pressure and temperature, and it's these increased pressure and temperature conditions which kind of open the window for deformation to begin, and metamorphism, come to think of it. So it's in this region down here that we're going to be focused on during the next few lectures. Now of course once you've formed our metamorphic rock, of course you can uplift it and you can erode it, or you can keep burying it. If you bury it and get the right conditions, you can make the rock melt, of course producing magma. That magma will of course solidify, producing an igneous rock, which of course you can then uplift and erode all over, and then the cycle starts all over again. So we're very familiar with this diagram by now. Alright, so let's have a look at this picture here. Well, this is a picture of the Appalachians, and if you've ever been on Google Earth and looked at the Appalachians, what you'll realise is that the pattern you can see in the picture in front of us is actually quite common. So the Appalachian area is well known for having these parallel, rather steep-sided valleys. In the bottom of each of these valleys there'll typically be quite a small stream running along the bottom. So these valleys run parallel to each other, and occasionally you'll see two parallel valleys will actually come towards each other and they will actually join up to produce a point, and you can see lots of these points on this diagram if you have a very careful look. They're all over the place. So the question becomes well, what are we looking at here? Well, obviously you can probably work out, bearing in mind the class you're taking, the answer to this is geology based. So what we're looking at here is we're clearly looking at some kind of process that is, doing something to the crust to produce this pattern. So the question is what are we looking at? Well, the result is we're looking at deformation. And so what kind of deformation are we looking at, and how is that deformation being achieved? Okay, so let's have a think. Well, what we're going to do is we are going to start off with a layer of rock. Alright, so this rather chunky blue line is our layer of rock. Yep, spared nothing on the animation. Okay, and what we're going to do is we are going to compress our layer of blue rock from either end, and of course that is going to cause our layer of blue rock to buckle. It's going to fold. And so our layer of blue rock that was quite long has been compressed, so now it's this long, but of course it's folded. So we've decreased the length of it, but we've increased the height. So what's going to happen now? Well, of course now we have our layer of folded blue rock. So eventually erosion will kick in, and the top of that layer of blue rock gets eroded away. And that black line, this black line right here, now represents the surface of the Earth as it is now. And so what we have here is, you can see this blue layer of rock keeps appearing again and again and again and again and again, because it's been folded. Now imagine there's a situation where this blue layer of rock is actually quite weak and easily eroded. And so what's going to happen? Well, obviously the layer of rock is going to get eroded. It's going to preferentially allow water to move along this weak layer. The movement of water along this weak layer is going to start producing these very steep river valleys, which we can see in the picture above. And so if we were to look at a more realistic sketch of the Appalachian area, what would we see? Well, we would see this. This is a more realistic diagram of what we have in the Appalachians. And you can see, once again, if we assume this blue layer, for instance, is the layer in question that's very easily eroded, you can see because it's been folded, it appears again and again and again and again and again, and so on. Just like this layer of rock here, which is clearly being eroded again and again and again, producing all of these river valleys. And so what we're seeing here is a really big surface expression of the process of deformation. Alright, so what is the process of deformation? Well, during deformation, rocks are squeezed, stretched, sheared, or broken. So deformation occurs in one of two types. There is what's referred to as brittle deformation, where the rock breaks and you can't repair it. So think of like dropping a glass on the floor. That's brittle deformation. The glass breaks, you can't put it back together. And then we have what's referred to as ductile deformation. That's when the rock will fail, it will flex, it will fold, but you can't put it back in its original form. So once it's bent, you can't go back. And just imagine if you were to take a piece of copper, for instance, and you were to bend it, and you can't get it back to its original position. Once you've bent it, you've done the damage, and it's there, and that's it. So what are we going to be looking at? Well, we're going to think about, to begin with, the ideas of stress and strain, because they're very, very important to deformation. We're then going to think about the type of deformation structures that we can produce, because there's two main groups, folding and fractures. We're going to think about deformation and its place in plate tectonics, and then we're going to eventually come on to geologic mapping, but that's kind of more to do with the lab, to be honest. Okay, so when it comes down to deformation, the first thing you need a force. So a force is essentially a push or a pull expressed as amount of acceleration experienced by a mass. So if our mass is at this ball of stone here, and in order to make that ball of stone move, we have to apply a force to it. And that's it. We're just applying a force to a body of material. Now, if we look at this diagram here, what we have is we have the same amount of mass. So you can see we have this steel disc here. Now in this case we can see the steel disc is placed upon a wooden post which has the same diameter as the steel disc. So we can see that the force, the mass of this steel disc, is being evenly distributed across quite a large surface area. So in this situation we can see the wooden post is perfectly capable of taking that weight. Now let's compare it to this situation over here. Once again, the steel disc has not changed in size, so the mass is still the same. However, the wooden post that it's resting on, as you can see, is now considerably thinner. This means the force of this steel plate is now distributed over a much smaller surface area, and so that means the force is concentrated, and so obviously that means that what we have here is a wooden post that's failing because of because the force is just too high. So what we're looking at here is stress, and stress is force per unit area. And so when it comes down to it, deformation is based on stress. In order to make a rock fail, obviously we need to reach the point where we're exceeding the strength of the layer of rock, don't we? And so we need our force per unit area to exceed the strength of our layer of rock. And once that happens, our layer of rock can either break in a brittle fashion, or it can begin to deform in a ductile fashion. So next of all, let's have a think about the different kinds of stress. Well, stress comes in two varieties. Now, the first type of stress is what's referred to as a confining stress. And this is when the amount of stress is equal from all directions. And this is, pretty much akin to the kind of stress that we're under. So, as I'm sitting here, or, you're standing there, wherever you are, you're sitting somewhere, you're being essentially pushed from the sides, you're being pushed from top and bottom, you're being pushed front and back. But those stresses are pretty much equal. And so that means that, you're not getting squished, you're not getting squished, you're not getting squished. Essentially, because everything's equal, nothing happens. So confining stresses is essentially what we have, what is kind of a case of equilibrium. Nothing changes because the forces are equal in all directions. Now, in the case of the next type of stress, which is called differential stress, the forces are not equal in all directions. So here's an example of differential stress where you can see that in this instance the stresses coming from here and here are considerably stronger than the stresses coming top to bottom and front to back. And so this means this particular cube of rock is obviously going to be squished. So it would be like me sitting here and then somebody putting a 2-ton weight on top of my head. Well, obviously there's going to be a differential stress, isn't there? The 2-ton weight's obviously going to start pushing down on me, and poor old Dr. White's going to get flattened like a pancake. So that's an example of a differential stress. So in order to deform rocks, we need a differential stress. So if our rock is in an environment where it's under a confining pressure, so the forces are equal in all directions, our piece of rock is just going to sit there. Nothing's going to happen to it. However, if we actually want to start deforming our rock, what we need to do is we need to get our rock under a differential stress, and so we need to have greater forces coming from some direction to begin to make our rock begin to deform. So differential stresses will obviously result in the following kind of situation. So here we have ourselves just a circle, and you can see within this circle we have these black lines, and they're representing a kind of a kind of platy mineral, something like biotite, if you remember, that very highly reflective black mineral that we see. You can peel it very, very easily, if you remember. It was kind of like pages in a book, for want of a better way of describing it. Now, in this situation, as you can see, the pressure is uniform in all directions, so it's under confining pressure. And you can see this circle is perfectly happy because there's no excess pressure coming from any one direction. Now in this situation on the right here, what you can see is the circle has been exposed to a differential stress. The pressure coming from left and right is greater than the pressure coming from the bottom and top. And so what you can see is our circle has been deformed into an ellipse. But the result of this process happening is all of these randomly orientated black crystals have all begun to crudely align themselves, haven't they? And what you can see is, there's a very crude alignment going from top to bottom, isn't there? Essentially at 90 degrees to the direction in which the rock is being squished. So the rock is being squished left to right, and these minerals are aligning themselves top to bottom. And so what you're seeing here is the very early stages of what in geology we refer to as a fabric. And a fabric is the result of deforming a rock. If you put the rock under pressure, some types of mineral will naturally start to align themselves in the same orientation, which will produce a layering to your rock, which is described as a fabric. So this is one of the ways which we can see the results of differential stresses, on a piece of rock. Okay, so let's just have a think about our piece of rock. So if you look here, we have a square piece of rock, and we're applying a small stress to it. Well, rocks are amazingly robust things, and so if you apply a small stress to a rock, nothing's going to happen. It's just going to sit there. So as we begin to increase the stress on our rock, well, once again, rocks are surprisingly robust things, and so it's just going to sit there. Eventually, though, we are going to put too much stress on the rock, and our rock is going to fail. And so you can see in this case, our rock has failed in a brittle fashion, and it's begun to crack. Of course, rock can also fail in a ductile fashion, and it can begin to flex and bend. So what we have to do is we have to make sure our rocks are exposed to sufficient stress to begin to make them fail. If we don't reach that point, our rocks will not fail, and they will just stay the way they were. So the first question is, well, how do we make rocks fail? Well, the first thing we need to think about is, where are we in the crust? So if we look at this very simplified diagram here, what can we see? Well, we can see that we have depth here on the y-axis and increasing strength here on the x-axis. And you can see as we go from here to the right, we can see the strength of the rock is increasing. And as we go from here downwards, the depth is increasing. And you'll see on this diagram we have ourselves 3 zones. We have a zone here in blue marked brittle. We have a zone here in kind of pinky peach marked ductile. And we have a kind of transitional field in between called the brittle ductile transition. So what are we looking at? Well, we're looking at how a rock will behave as it gets deeper in the Earth's crust. So let's imagine we have a piece of rock and we're starting right here on the Earth's surface. Okay, well, right here on the Earth's surface, pressure is relatively low, the rock is relatively strong, so nothing's going to happen to the rock. The rock is perfectly happy. Okay, so as we take our piece of rock deeper and deeper and deeper into the crust, what's going to happen to it? Well, to start with, as it gets deeper, the pressure is going to start getting higher. And as that pressure starts to squish on our piece of rock, okay, it starts to make it stronger. Because as you're compressing the rock, you're starting to make it into a more and more compact unit. And so as you take your piece of rock deeper and deeper in the crust, the first thing that happens is you compress it and it begins to get stronger. Now that means, well, there's one more thing, sorry, I should say. Also, in the brittle area of the crust, well, it's not actually that hot. It's quite cold. So your rock in this area will also not be that warm, geologically speaking. So what you have here is you have cold rock, which is under a lot of stress, so it's really quite strong. And so if you're going to make your rock fail, because it's cold, it's going to behave in a brittle fashion. It's going to crack. Okay, so we're going to get something that looks like this picture down here in the bottom left. Now, as we keep getting deeper and deeper and deeper, eventually we're going to reach a point where the temperature starts to get higher. And as that temperature starts to increase, our rock is now going to start to weaken. So why is that? Well, as the temperature begins to get higher, of course, if you remember from high school chemistry, as the temperature begins to increase, the atoms in a material will begin to vibrate faster and faster and faster. Now, as the atoms begin to vibrate faster and faster and faster, that leads to the bonds in between those atoms beginning to weaken. And so it means the atoms can now start to move a little bit relative to each other. So the atoms that were once held in a really rigid structure and they couldn't move are now able to move a little bit. And so our material that was solid all of a sudden finds itself a little bit ductile. It can begin to flow, it can begin to bend and flex. And so when we reach the point where temperature starts to get a bit higher, well, what do we see? Well, to start with, we can see the strength of our rock begins to decrease. And that's because our rock is no longer behaving as a solid unit, it's now beginning to become flexible. And so we see our strength begin to drop. And now because we're beginning to see the strength of the rock drop, it's no longer going to behave in a brittle fashion, it's now going to start to behave in a ductile fashion. You can now make the rock flex and bend and fold and stretch. And so, as you can see, depending on temperature primarily, we have these 2 zones in the crust. We have the brittle zone at the top, where our rock strength increases, and the rock is cold, and so it will fail in a brittle fashion. And then in the lower portions of the crust, the rock starts to get quite hot. It starts to behave in a more ductile fashion, and so our rock will begin to flow. It will begin to bend and flex. And so the brittle zone is typically about the top 10 kilometers of the Earth's crust. This brittle ductile transition is taking place in about the 10 to 15 kilometer range, and then typically from about 15 kilometers downwards, we're in the ductile field. And so that's what this diagram is, trying to show you in a very simplified way. Okay, so what are our 3 types of differential stress? Well, the first type is a compressional stress, and this will lead to what's referred to as shortening. So our piece of rock that was this long is shortened and is now this long because we've compressed it. Obviously, that's going to be caused by a compressional force. The next force is what's referred to as tension. or we'd sometimes refer to it as extension. So in the case of tension, our rock is going to be stretched. And so this is going to lead to our piece of rock being stretched and increasing in length. The final type of force that our rock can be exposed to is shear. And that's when we're taking our piece of rock and we're trying to pull it in two directions simultaneously. We're dragging it out, drawing it out. So these diagrams kind of summarize the process. Now the resolution is absolutely horrendous, but they do get across the situation quite nicely. So what you can see here is we have a situation where we have compression. So these layers of rock were initially a lot longer, but they've been squished, and now the layer itself, which was, maybe started here and went to here initially, so from this point to this point, has now been squished. So the layer itself has gotten shorter, hasn't it? It's now from here to here. So the length is shortened. However, the height of the layer has increased because the layer used to be just this thick. So the thickness from here to here. But now, because we've compressed the layer, the thickness is now from here to here. So essentially we've doubled the thickness of the layer by folding it, haven't we? So the layer's become shorter, but it's become thicker. Now in the case here of tension, what happens? Well, we have our layer and we start to stretch it. Now, you'll be familiar with what happens with tension if you've ever had anything like silly putty and you started to pull it. You'll know as you start to pull with silly putty, the layer gets thinner and thinner and thinner and thinner the longer and longer you make it, and eventually it snaps. So during tension, what happens is you begin to stretch the layer of rock. This layer will get thinner and thinner and thinner the more and more you stretch the rock. So we're familiar with that bit of mechanics already. And then we have shearing. And you can see in the case of shearing, you're not really going to change too much actually. You're not going to make the layer thicker. What you're going to do is you're going to end up trying to make, as you can see in the case of this diagram, one part of the sequence go one way and one part of the sequence go the other way. And so these two layers here will probably actually remain relatively undeformed. It's this poor old brown layer in the middle. That's the one that's actually going to get quite stretched as the beige layer at the top goes to the right. The grey layer at the bottom goes to the left. It's this brown layer in the middle here that has to actually accommodate the movement, and it's that layer that's got to be stretched out to make that happen. Okay, so how do rocks respond to differential stress? Well, we've already gone and touched on the fact that rocks by their nature are very, very robust things, so if you apply a small amount of differential stress to them, nothing happens. No, nothing. However, if you manage to apply enough stress to them, one of three main things will occur. The first one is what we refer to as displacement. And so displacement is a brittle feature of deformation, so it's not ductile, it's brittle, and it's produced by pieces of rock moving. So as you can see, this piece of rock here started in this position, it has now been displaced, and you can see it here in this position. And so we can see displacement on this diagram right here. So you can track this white layer of rock right here, and you can see that this block of rock here has displaced upwards relative to this block of rock over here. This block of rock here has displaced upwards relative to this block of rock over here. So this is displacement. What else can happen? Well, the next thing that can happen is rotation. So as you can quite clearly see, these layers of rock here are tilted. Now, as we've already gone and discussed, the principle of original horizontality clearly states that a layer of rock will initially be deposited as a horizontal sheet. So if our layer of rock is not a horizontal sheet and it's being tilted, well, clearly something's caused that layer of rock to rotate, hasn't it? So differential stresses can also lead to our layers of rock rotating. Now this can be a brittle feature, or it can also be a ductile deformation feature. Finally, we have strain. So strain is the final response to differential stresses, and strain is primarily a ductile feature. So in the case of strain, what you can see is we initially have our block of rock, and it's a flat rectangle, and as we compress it, the rock will begin to deform, and this flat rectangle, as you can see, turns into an upright rectangle. And it's just essentially, there's no change in volume. All that's happened is the layer of rock has just been compressed from the sides, and obviously it's caused it to thicken. And we discussed that earlier when we were discussing, compression about one slide ago. So this is primarily a ductile feature, as it requires the rock to flow, doesn't it? I mean, you can't really do this if your rock is behaving like a brittle material, because it will just crack. So in order for this to happen, you really need your rock to be able to flow, so it needs to deform in a ductile fashion. So these are our three responses. So if you apply stress to a layer of rock, you can either cause it to displace, rotate, or you can cause it to suffer strain, in which case it will deform. Okay, so our types of strain, well, we've already touched on two of them already, but there is actually a third type of strain. Now, this third type of strain is called elastic strain, and we're not really going to worry about it too much, because elastic strain isn't too big in geology. Elastic strain is only important really when it comes to earthquakes. That's when elastic strain really comes into its own. So what is elastic strain? Well, elastic strain is this. So here I have my ruler, my trusty ruler, which if I break it, I'll be really annoyed. So I'm going to take my ruler and I'm just going to squish it from either end, and you can see my ruler is going to flex. So it's bending. So I'm applying force to my ruler and it's bending. Now, the fact my ruler is bending is storing the energy that I'm putting into the ruler, but the second I let the ruler go, the ruler snaps back to its original position, and it's now gone back to its original shape. That's elastic, and that's elastic strain. I'm putting strain onto a material, I'm causing it to deform, but as soon as that strain is released, the material returns to its original shape. Okay? Now, this doesn't work for either brittle or ductile deformation, does it? So elastic strain isn't really that important to us. We're concerned with ductile and brittle deformation. So in the case of ductile deformation, our material will deform, so it will fold, it will flow, but it will not return to its original shape. Once it started deforming, that's it. It can't go back to the shape it started with. And then we have brittle deformation. Well, obviously, in the case of brittle deformation, it will fail in a brittle fashion, it will crack. And obviously, as I'm sure you know, once you drop a glass on the floor, you can't put it back the way it was. So, elastic, ductile, and brittle don't correspond to each type of stress, so don't get caught out by that, okay? So, just one second, went too far there. Elastic, brittle, and ductile do not correspond to these types of differential stress, so don't get the two confused, okay? Alright, so do you know what? This is probably a really good time to stop stop this first video. So once again, please get up, have a walk around, get a glass of water, coffee, tea, and come back when you're ready for part 2.